Okay, so for Unit 5, some main constants that we went over were the centripetal force. So for an object that's moving in a circular path, they experience a force inward, which what we call it is the centripetal force. It's technically what we call like a fake force because you can't write centripetal force on a free body diagram. It doesn't exist. It's a different force. So for example, force gravity or force normal can be centripetal force, but you can't directly write the force centripetal in a free body diagram. We also went over briefly about escape velocity and how escape velocity doesn't rely on mass. So whatever object is being projected from Earth, whether it's a rocket or a molecule or a pencil, whatever, they all have the same escape velocity since mass doesn't matter in that case. And then the last thing we went over, or the third thing for me, is torque. So torque equals RF sine theta, and we learned the right hand rule where you point your hand in the direction of R, and then you curl it in the direction of the force. And whether your thumb is pointing inward or outward, you can determine whether the torque is negative or positive.
Yeah, and just to clarify on a couple of things, we found out the escape velocity using conservation of energy, where we put UG as so far away where it basically like doesn't exist, and then we use kinetic energy as like the initial energy, and that's how we solve for escape velocity. And then some other concepts that we learned was gravitation. So instead of like in conservation of energy or just regular force gravity, we learned that force of gravity, like the real force of gravity, is equal to big G times the mass of the objects. That's the two objects that are experiencing the gravitational force. So most of the time, the first object would be the Earth because we experience Earth's gravity, and the second object would be the masses of these objects. The second mass would be the mass of whatever object is experiencing the Earth's gravity. And then that would just be over big R squared, where R is the radius between the Earth's center of mass. Most usually, it could be other planets or other objects as well, but most usually it's Earth squared. From the center of mass to the surface squared. And then we also talked a little bit about Kepler's laws, and that kind of has to do with the fact that Earth isn't a perfect circle. It's ovaled a little bit, and so Kepler's laws kind of give you a way to calculate the eccentricity, or how oval a rigid body or planet is, and it does so comparing the half of the length in the oval direction over like a fraction of the distance in the vertical direction to get an eccentricity. And then I believe what was the other concept that I talked about?
Shell theorem.
Oh, and then shell theorem was the other big concept in this unit. Well, I wouldn't say big, but important concept that was new to both of us. It basically just states that in a hollow body, wherever you are in a planet that's a hollow body, you will experience no gravitation. It's kind of interesting, but the formula for Newton's shell theorem is just big G times the mass of the object that's producing the gravity times the mass of the object that's experiencing the gravity over R cubed, where R is the distance from the center of mass to surface, times little r, where little r is a ratio of big R. And yeah.
So for our Unit 5 practice problem, here we have a practice problem about torque. So I'll go ahead and read the question. A hungry bear weighing 700 newtons walks out on a beam in an attempt to retrieve a basket of food hanging at the end of the beam. The beam is uniform, weighs 200 newtons, and is 6 meters long. The basket weighs 80 newtons. Part A is asking to draw a free body diagram for the beam. So first, let's take a look at the beam. As we can see right here, we could already see that there's a force tension going upwards. The beam has its own gravitational force. So right here, where the center of mass would probably be, we'll name it, the beam will be mg1. So let's name it mg1. Where the bear is standing, the bear will have its own force gravity too, so mg2. And the basket over here on the edge of the beam will also have its own, so we'll do mg3. So we're going to go ahead and draw the free body diagram. We have a straight line representing the beam, and we have force tension going up, mg1 going down, mg2 over here, which we'll go take ahead and look at the Newton. So the bear weighs 700, the beam weighs 200, and the basket weighs 80. So I'm going to draw it respective. So the bear is the heaviest, so the bear will be the longest, mg2. This is the second longest since it's the second heaviest, and the basket is the lightest. So we're going to do mg3. And I almost forgot, but there's also a hinge keeping up the beam. So it's going to be opposite of the force of where everything's going to keep it up. So it's going to be this way, and this will just be our force hinge. So let me draw that in the force body diagram. It's going to be opposite of the force tension. It's going to be like that. Name it force hinge. Next, now that we have solved for part A, we want to do part B. So it says, when the bear is at x equals 1 meter, find the tension in the wire and the components of the force exerted by the wall and the left end of the beam. So first, we're going to solve for the tension. We know that now the bear is at, we're going to set our axis of rotation right here. The bear is 1 meter away, but to solve for the tension, we're going to first start with the net torque equals 0. So we're going to list all of our torques. The torque of the hinge does not exist since it is on the axis of rotation, so the R would be 0, therefore no torque. So we're going to write the torque of the bear. So R sine of theta, where it's F force R. So mg2 R sine theta, and that would be a positive. So all the ones going down, if you do the right hand rule, it's going to end up being positive. So mg2 r sine theta is positive, plus mg1 r sine theta is positive, plus mg3 r sine theta, and then I'll just write it over here where it's negative force tension r sine theta. All of this equal to 0. Since we could see that the gravity makes a 90-degree angle, therefore with the axis of rotation, therefore the torque would be, therefore sine of 90 equals 1. So all of these are being multiplied by 1, so you could just cancel it out. So 1, cancel, 1, cancel, 1, cancel. We want to take force tension, the torque of force, to the right side so we can isolate for force tension and then solve. So we're going to do that by adding force tension r sine theta to both sides. So we're going to get it mg2r plus mg1r plus mg3r equals force tension r sine of theta. Now the last move to isolate for force tension would be to divide r sine theta, and this is the r of the tension. So I guess I'll write it RT. Since this is mg3, they all have different radiuses or distances away from the axis of rotation. So R3, all right, R1 and R2, just to make it neat. So we're going to divide it to both sides. RT sine theta. Now, as our final result, before we plug all of our numbers in, you get mg2 times R2 plus mg1 times R1 plus mg3 times R3. All of this divided by R T sine of theta. We know that theta is 60 and the tension makes a 60-degree angle, so just write it as sine of 60. And then the rest, we know that mg2 of the beam equals 200 newtons, which is given in the problem. Then mg1 of the bear is equal 700 newtons, and mg3, which is the basket, equals 80 newtons. Now we're going to have all those numbers and multiply it by their distances away from the axis of rotation. So for the beam, mgr2 would be the distance of the beam, which is 6 meters divided by 2, so 3. For mg1, the bear is, it gives us here in part B that the bear is 1 meter away, so it's 700 times 1. Then for mg3, the basket is at the opposite end of the axis rotation of the beam, so it's 6 meters away. And same thing for the tension, it's also 6 meters away. So knowing all those, just looking at the problem, we don't have to solve for anything, it's all given. We get that the force tension equals 342.58 newtons. Now for the second part of part B, it asks to find for the components of the force exerted by the wall or exerted by the hinge on the left end of the beam. So we're going to start this by splitting up the forces in two parts, the net force in the y and the net force in the x. They're both going to be equal to 0 since everything is stationary. So first, starting off with the net force in the y, we could look at the free body diagram. Yet the force of the hinge in the y direction, we don't have to write sine theta or anything because all we're finding is that it's y component, which is what the question is asking. So we get force of the hinge in the y, that's upwards, which is our positive direction, minus all of these forces, mg2, mg1, and mg3, minus mg1, minus mg2, minus mg3. And then our last force would be plus force tension. And then since we have our theta here, which is 60, force tension sine of 60, since sine would be opposite. So force plus force tension sine of theta, all of this equals 0. So now looking at this, we're solving for force hinge in the y direction, so we want to isolate for that. So I'm going to keep force hinge on the y direction on this side, and I'm going to make it equal to, add all of these to the other side and subtract force tension sine of theta. So you get mg1 plus mg2 plus mg3 minus force tension sine of theta. Now, we all know this because we have previously saw for it in also part B, force tension, 34.258 newtons, then sine of theta 60, mg1, which is the force gravity on the bear, 700 newtons, mg2, which is the beam, 200 newtons, and mg3, the basket, 80 newtons. All of this stuff has been given to us. So knowing all that, if you were to plug it all in, then you get that the force hinge in the y direction equals 683.12 newtons. Now, since the question is asking for both the components, it's the same process for what we did for the y component, but now we're going to be doing it for the x. So you get net forces in the x direction equals 0 since the system is stationary. So we look at what's giving a force in the x direction. All of the mg's are not, but the force hinge is. But since we're solving for it in the x component, we don't have to add cosine theta or anything, so it would just be force hinge in the x. We're going to make that our positive direction, and then the force tension is opposing it, and we're going to make that the negative direction. So you get force tension cosine of 60. So I'm just going to write force tension cosine of theta. I'm not going to plug anything in yet. Equals 0. You're going to add force tension cosine theta to the other side. You get the force of the hinge in the x direction equals force of tension cosine theta. We saw for the force tension previously, so you take this number, plug it in here, you get cosine of 60, which is given in the problem. Knowing all those things, plug it all in, you get that the force hinge in the x direction equals 171.29 newtons. So now for part C, the final part, it says, what if the wire can withstand a maximum tension of 900 newtons, what is the maximum distance the bear can walk before the wire breaks? So I want to start this problem off with the net torque equals 0. We're keeping our axis of rotation on where the hinge is at, so the hinge does not have a torque since R is 0, therefore no torque. So we're going to look at all the other torques. We had already done this in the previous problem, so we're just going to rewrite what we did for part B. We're just going to do it for part C now. So now we know that it's negative torque tension plus torque mg1 plus torque mg2 plus torque mg3. With previous knowledge, we know that torque equals RF sine theta, so we're going to rewrite everything as negative R. I'm going to write FT as just T sine theta plus R mg1 sine theta plus R mg2 sine theta plus R mg3 sine theta. Now I forgot to write, but I'm going to label each R since they're all different. So R3, R2, R1, and I'm going to write RT, or the distance away as tension as RT. What we did before, we know that the sine theta, theta is 90, therefore sine is 1, so we can cancel it out. Now we get negative RT, T sine theta, plus R1 mg1, plus R2 mg2, plus R3 mg3 equals 0. Forgot to write 0 on all of these, but all of this is equal to 0. We want to solve for how far the bear can walk, so it's going to be RT. Oh, no, sorry. It's going to be R1. We're solving for R1. So we want to isolate for RT first so that we can get everything to its own side. So we're going to get R1 mg1 plus R2 mg2 plus R3 mg3 equals RT T sine theta. Now, in order to isolate for R1, we're going to have to subtract R2 mg2, R3 mg3, and then divide all that by mg1. So we're just going to do that. It's going to be one big equation. So we get RT T sine theta minus R2 mg2 minus R3 mg3 all over mg1 equals how far the bear could walk out. So we know that RT, since tension is on the opposite side of the beam, is 6 meters. T, which was given to us in the problem last time, what was different in part B is that we had to solve for tension, the force tension. But this time it says a maximum tension of 900 newtons. So now we know that the force tension equals 900 newtons. Sine of theta, theta is given as 60, so sine of 60, minus R2, which is the beam. So the beam is 6 meters long, so 6 divided by 2 would be 3 meters away from the axis of rotation. The force gravity of the beam is given as 200 newtons, and since the basket's at the opposite side of the beam, it's 6 meters, and the force gravity of the basket was given at 60 newtons, all divided by mg1, which was given for the force gravity on the bear, which is, I believe, 700 newtons. Yes. So plugging all these in, everything that was given to us, you get that R1, or the distance, the maximum distance that the bear can walk with the tension being 900 newtons, is 5.13 meters. And that is the whole problem. So for this unit, there was no investigation or lab. So nothing to talk about for that section.
Yeah.
We talked about what stood out to us. Torque was something not new to us, but Newtonian gravitation was, and Shell theorem and all that. But